decision of sine and cosine functions of an initial equation, and really just analyze them here. So we will notice that they have difference in amplitude, same period, however, one's a cosine, one's a sine function, and their sum also has sort of attributes of both, right? It's close to a cosine function, but horizontally shifted, so that it's not. And then you'll notice an amplitude here. It is an increase in amplitude when we add those. And so we wrote this equation in the form of cosine, or in terms of cosine. For A equals amplitude, B equals the period of the parent function divided by the period of the graph, and C is a phase shift, or a horizontal shift. 2.94 rate shift to the right, 3.606 amplitude. Now the period is still up high. And so when you add these two together, you'll notice they still have the same period. So when adding graphs, you cannot change the period, but you may change the amplitude as well as phase shift. And of course, contrast, you'll notice there is a difference in amplitude. Proving identities, this is really the form of the first function we created for the situation. And this is the cosine terms, same version of that function. So we factor out our amplitude, using the property of addition and multiplication, which is the ability to manipulate, move the operands, operators in a calculation. This is 5 plus 3 is 8, 3 plus 5 is 8, 5 times 3 is 15, 3 times 5 is 15. So addition and multiplication, we use the property still applies, and then we apply our difference identity for cosine. So we also write our original equation in terms of cosine. That is the case here. I'll speak one only. Write the proof here. That's where it actually comes together. You'll notice that this has the same function, validating the identity that we just proved. If you calculate square root of 13, it is roughly 3.606. So our question is, this assignment as well as the course have dramatically changed my perspective of trig. Initially thought trig would be a field of mathematics that dealt with spatial problems and anything else, and it still very much does. But also has several more applications than I ever thought initially. Being electrical engineering major, I thought I would try to find an example of my spring system that is frequently used in the field. However, I wasn't really able to find one. It seems like it's more of a mechanical engineering concept in terms of movability. However, despite that, EE is filled with tons of sinusoidal functions, waveforms, studying of alternating current. So there are plenty of analogies we can have for this. And in this case, we'll be doing an RCL circuit. So what is an RCL circuit? An RCL circuit is also known as a tuned circuit. An electrical circuit consisting of a resistor, an inductor, and a capacitor in series or in parallel. In this case, we'll be doing series. It is also known as a harmonic oscillator, which is a system that, when displaced from its equilibrium position, experiences a restoring force proportional to the displacement. For this example, we will use a series version of the circuit. So there's 3 basic elements to both a mass spring system as well as an RCL circuit: mass, spring, and friction for a mass spring system. With an RCL circuit, we have inductors, capacitors, and resistors. And we will compare and contrast the two in the following slide. Inertia and inductance. So mass has what's known as inertia. It's property of matter. That is that resistance to a change of state, or physical state. So with mass on the end of the spring, let's apply some force over a distance to further our displacement and ultimately cause motion that is sinusoidal and measured over time. Due to inertia, an initial resistance to the movement of the mass, but once this mass is set in motion, its momentum, while building it, while moving the mass, it will build momentum. Once we let go of that mass, quit inputting some kind of force, that momentum will stabilize. It will perpetuate that motion, as well as the springs. They work collaboratively. So that is one of the factors that dictates the amplitude of this motion. So it is important to understand the role that mass plays on the system to effectively design a spring system for some function. Inductors have what's called inductance. And so that is causes electromotive force to be generated by a change in the current flowing. Right? So it's kind of like building momentum, a kinetic force being built by a change in current which then obviously presses that thing to build force. So this force resists a current at first, but it will, the longer a current continues to oscillate through or on it, conductivity will increase and it will ultimately allow current to flow through it. And much like momentum of inertia and mass, it helps perpetuate that motion, perpetuate that frequency. It resists changes to frequency. So springs. Springs have elasticity. The stiffness of a spring is determined by how elastic that spring is. So with a spring, if we begin to apply some force over a small distance, it'll be very easy to move it first. But the more force and distance we apply and cover, the harder that spring becomes to expand or contract to this point of equilibrium. So what the spring is doing is storing energy, or potential energy in this case. So the closer we reach to the spring's maximum ability to store energy, the more the spring will output an opposite force against the one we are inputting. So of course, if we release the spring, say for example, if we press one into the ground and move our hand very quickly, all that potential energy would rapidly release and that spring would rapidly expand, causing it to shoot off very much like a rocket. So the spring's elasticity not only affects amplitude, but also the frequency of the wave, or the wave's period. Capacitors. So capacitors have capacitance, which is the ability to store an electric charge. In this case, again, potential energy. So when charging a capacitor, charge increases frequently at first. The closer you get to the capacitor's capacitance, much like pressing a spring to its maximum contraction, the more that capacitor resists being charged. In fact, it approaches the vertical asymptote, meaning it impulse slows down in its rate of charge, but never quite hits its maximum capacity or capacitance. So just like the spring, the capacitor is storing potential energy and is outputting a resistance force against the voltage input. Also, just like the spring, the moment the input voltage is lost, the capacitor rapidly discharges. Its potential energy then becomes kinetic energy. So capacitors, too, can affect the amplitude and frequency of an alternating current going through them. Last but not least, friction resistance. So friction in a real spring system, granted in this case, or our project, we neglected that, but that could be gravity, that could be air resistance, etc. Friction is something that has to be considered, much like a mass dropping from a height attached to a spring. Once it falls to the maximum drop of the wave, it will rebound. However, other forces prevent this rise and fall in height from perpetuating forever. So yeah, that's kind of that role in that. The RCL circuit's resistors also called restriction. So resistors are used in collaboration with the rest of the devices in the circuit to absorb all frequencies that are not sought after. For example, in an AM/FM radio, they absorb frequencies besides the narrow range we tune to using a variable capacitor. And so that's it. That's the analogies. It's important to understand amplitude, phase shift, frequency, not only in mass spring systems, but as well as in the context of don't know everything about these circuits. That's me with my professor, Jamie.